Hello and welcome to this lecture. In this lecture, we look at container networking interface. So far, we saw how network namespaces work, as in how to create an isolated network namespace environment within our system. We saw how to connect multiple such namespaces through a bridge network, how to create virtual cables or pipes with virtual interfaces on either end, and then how to attach each end to a namespace and the bridge. We then saw how to assign IP and bring them up. And finally, enable NAT or IP masquerade for external communication, etc. We then saw how Docker did it for its bridge networking option. It was pretty much the same way, except that it uses different naming patterns. Well, other container solutions solve their networking challenges in kind of the same way, like Rocket or Mesos Containerizer, or any other solutions that work with containers and requires to configure networking between them, like Kubernetes. If we are all trying to solve the same networking challenges by researching and finally identifying a similar approach with our own little minor differences, why code and develop the same solution multiple times? Why not just create a single standard approach that everyone can follow? So we take all of these ideas from the different solutions and move all the networking portions of it into a single program or code. And since this is for the bridge network, we call it bridge. So we created a program or script that performs all the required tasks to get the container attached to a bridge network. For example, you could run this program using its name bridge and specify that you want to add this container to a particular network namespace. The bridge program takes care of the rest so that the container runtime environments are relieved of those tasks. For example, when Rocket or Kubernetes creates a new container, they call the bridge program and pass the container ID and namespace to get networking configured for that container. So what if you wanted to create such a program for yourself, maybe for a new networking type? If you were doing so, what arguments and commands should it support? How do you make sure the program you create will work correctly with these runtimes? How do you know that container runtimes like Kubernetes or Rocket will invoke your program correctly? That's where we need some standards defined. A standard that defines how a program should look, how container runtimes will invoke them so that everyone can adhere to a single set of standards and develop solutions that work across runtimes. That's where Container Network Interface comes in. The CNI is a set of standards that define how programs should be developed to solve networking challenges in a container runtime environments. The programs are referred to as plugins. In this case, Bridge program that we have been referring to is a plugin for CNI. CNI defines how the plugin should be developed and how container runtimes should invoke them. CNI defines a set of responsibilities for container runtimes and plugins. For container runtimes, CNI specifies that it is responsible for creating a network namespace for each container. It should then identify the networks the container must attach to. Container runtime must then invoke the plugin when a container is created using the add command and also invoke the plugin when the container is deleted using the del command. It also specifies how to configure a network plugin on the container runtime environment using a JSON file. On the plugin side, it defines that the plugin should support add, del, and check command line arguments, and that these should accept parameters like container and network namespace. The plugin should take care of assigning IP addresses to the pods and any associated routes required for the containers to reach other containers in the network. At the end, the results should be specified in a particular format. As long as the container runtimes and plugins adhere to these standards, they can all live together in harmony. Any runtime should be able to work with any plugin. CNI comes with a set of supported plugins already, such as Bridge, VLAN, IPVLAN, MacVLAN, one for Windows, as well as IPAM plugins like Host Local and DHCP. There are other plugins available from third-party organizations as well. Some examples are Weave, Flannel, Cilium, VMware NSX, Calico, Infoblox, etc. All of these container runtimes implement CNI standards, so any of them can work with any of these plugins. But there is one that is not in this list: Docker. Docker does not implement CNI. Docker has its own set of standards known as CNM, which stands for Container Network Model, which is another standard that aims at solving container networking challenges similar to CNI but with some differences. Due to the differences, these plugins don't natively integrate with Docker, meaning you can't run a Docker container and specify the network plugin to use a CNI and specify one of these plugins. But that doesn't mean you can't use Docker with CNI at all. You just have to work around it yourself. For example, create a Docker container without any network configuration, and then manually invoke the bridge plugin yourself. That is pretty much how Kubernetes does it. When Kubernetes creates Docker containers, it creates them on the none network. It then invokes the configured CNI plugins who take care of the rest of the configuration. We talk about CNI in Kubernetes in the upcoming lectures. And welcome to this lecture. In this lecture, we look at the networking configurations required on the master and worker nodes in a Kubernetes cluster. The Kubernetes cluster consists of master and worker nodes. Each node must have at least one interface connected to a network. Each interface must have an address configured. The hosts must have a unique host name set, as well as a unique MAC address. You should note this especially if you created the VMs by cloning from existing ones. There are some ports that needs to be opened as well. These are used by the various components in the control plane. The master should accept connections on 6443 for the API server. The worker nodes, Kube Control Tool, external users, and all other control plane components access the Kube API server via this port. The kubelets on the master and worker nodes listen on port 10250. Yes, in case we didn't discuss this, the kubelets can be present on the master node as well. The kube scheduler requires port 10251 to be open. The kube controller manager requires port 10252 to be open. The worker nodes expose services for external access on ports 30,000 to 32,767. So these should be open as well. Finally, the HCD server listens on port 2379. If you have multiple master nodes, all of these ports need to be open on those as well. And you also need an additional port 2380 open so the HCD clients can communicate with each other. The list of ports to be opened are also available in the Kubernetes documentation page. So consider these when you set up networking for your nodes in your firewalls or IP table rules or network security group in a cloud environment such as GCP or Azure or AWS. And if things are not working, this is one place to look for while you're investigating. Head over to the practice session and explore the networking setup in the existing environment. Keep these commands handy while you look for information. We will start with simple exercises where you will explore an existing Kubernetes cluster and view information about the interfaces, IPs, hostnames, ports, etc. This will help you familiarize with the environment and look for information in the future sections. Going forward, we will get into more challenging exercises. For now, let's start slow. Hello and welcome to this lecture. In this lecture, we discuss about pod networking in Kubernetes. So far, we have set up several Kubernetes master and worker nodes and configured networking between them so they are all on a network that can reach each other. We also made sure the firewall and network security groups are configured correctly to allow for the Kubernetes control plane components to reach each other. Assume that we have also set up all the Kubernetes control plane components such as the Kube API server, the HCD servers, kubelets, etc. and we're finally ready to deploy our applications. But before we can do that, there is something that we must address. We talked about the network that connects the nodes together, but there's also another layer of networking that is crucial to the cluster's functioning, and that is the networking at the pod layer. Our Kubernetes cluster is soon going to have a large number of pods and services running on it. How are the pods addressed? How do they communicate with each other? How do you access the services running on these pods internally from within the cluster, as well as externally from outside the cluster? These are challenges that Kubernetes expects you to solve. As of today, Kubernetes does not come with a built-in solution for this. It expects you to implement a networking solution that solves these challenges. However, Kubernetes have laid out clearly the requirements for pod networking. Let's take a look at what they are. Kubernetes expects every pod to get its own unique IP address, and that every pod should be able to reach every other pod within the same node using that IP address. And every pod should be able to reach every other pod on other nodes as well, using the same IP address. It doesn't care what IP address that is and what range or subnet it belongs to. As long as you can implement a solution that takes care of automatically assigning IP addresses and establish connectivity between the pods in a node as well as pods on different nodes, you're good, without having to configure any NAT rules. So how do you implement a model that solves these requirements? Now, there are many networking solutions available out there that does these. But we've already learned about networking concepts, routing, IP address management, namespaces, and CNI. So let's try to use that knowledge to solve this problem by ourselves first. This will help in understanding how other solutions work. I know there is a bit of repetition, but I'm trying to relate the same concept and approach all the way from plain network namespaces on Linux all the way to Kubernetes. So we have a 3-node cluster. It doesn't matter which one is master or worker, they all run pods either for management or workload purposes. As far as networking is concerned, we're going to consider all of them as the same. So first, let's plan what we're going to do. The nodes are part of an external network and has IP addresses in the 192.168.1. series. Node 1 is assigned 11, node 2 is 12, and node 3 is 13. Next step, when containers are created, Kubernetes creates network namespaces for them. To enable communication between them, we attach these namespaces to a network. But what network? We've learned about bridge networks that can be created within nodes to attach namespaces. So we create a bridge network on each node and then bring them up. It's time to assign an IP address to the bridge interfaces or networks. But what IP address? We decide that each bridge network will be on its own subnet. Choose any private address range, say 10.244.1, 10.244.2, and 10.244.3. Next, we set the IP address for the bridge interface. So we have built our base. The remaining steps are to be performed for each container and every time a new container is created. So we write a script for it. Now, you don't have to know any kind of complicated scripting. It's just a file that has all commands we will be using. And we can run this multiple times for each container going forward. To attach a container to the network, we need a pipe or a virtual network cable. We create that using the IP-link add command. Don't focus on the options as they are similar to what we saw in our previous lectures. Assume that they vary depending on the inputs. We then attach one end to the container and another end to the bridge using the IP-link set command. We then assign IP address using the IP-addr command and add a route to the default gateway. But what IP do we add? We either manage that ourselves or store that information in some kind of database. For now, we will assume it is 10.244.1.2, which is a free IP in the subnet. We discuss about IP address management in detail in one of the upcoming lectures. Finally, we bring up the interface. We then run the same script, this time for the second container with its information and gets the container connected to the network. The two containers can now communicate with each other. We copy the script to the other nodes and run the script on them to assign IP address and connect those containers to their own internal networks. So we have solved the first part of the challenge. The pods all get their own unique IP address and are able to communicate with each other on their own nodes. The next part is to enable them to reach other pods on other nodes. Say for example, the pod at 10.244.1.2 on node 1 wants to ping pod 10.244.2.2 on node 2. As of now, the first has no idea where the address 10.244.2.2 is because it is on a different network than its own. So it routes to node 1's IP as it is set to be the default gateway. Node 1 doesn't know either since 10.244.2.2 is a private network on node 2. Add a route to node 1's routing table to route traffic to 10.244.2.2 via the second node's IP at 192.168.1.12. Once the route is added, the blue pod is able to ping across. Similarly, we configure route on all hosts to all the other hosts with information regarding the respective networks within them. Now, this works fine in this simple setup, but this will require a lot more configuration as and when your underlying network architecture gets complicated. Instead of having to configure routes on each server, a better solution is to do that on a router if you have one in your network, and point all hosts to use that as the default gateway. That way, you can easily manage routes to all networks in the routing table on the router. With that, the individual virtual networks we created with the address 10.244.1.0/24 on each node now form a single large network with the address 10.244.0.0/16. It's time to tie everything together. We performed a number of manual steps to get the environment ready with the bridge networks and routing tables. We then wrote a script that can be run for each container that performs the necessary steps required to connect each container to the network. And we executed the script manually. Of course, we don't want to do that, as in large environments where thousands of pods are created every minute. So how do we run the script automatically when a pod is created on Kubernetes? That's where CNI comes in, acting as the middleman. CNI tells Kubernetes that this is how you should call a script as soon as you create a container, and CNI tells us this is how your script should look like. So we need to modify the script a little bit to meet CNI standards. It should have an add section that will take care of adding a container to the network, and a delete section that will take care of deleting container interfaces from the network and freeing the IP address, etc. So our script is ready. The kubelet on each node is responsible for creating containers. Whenever a container is created, the kubelet looks at the CNI configuration passed as a command line argument when it was run and identifies our script's name. It then looks in the CNI's bin directory to find our script and then executes the script with the add command and the name and namespace ID of the container. And then our script takes care of the rest. We will look at how and where the CNI is configured in Kubernetes in the next lecture along with practice tests. For now, that's it from the Pod Networking Concepts lecture. Hopefully that should give you enough knowledge on inspecting networking within pods in a Kubernetes cluster. We will see how other solutions do the same thing that we did in the upcoming lectures. Hello and welcome to this lecture. In this lecture, we will discuss about CNI in Kubernetes. In the prerequisite lectures, we started all the way from the absolute basics of network namespaces. Then we saw how it is done in Docker. We then discussed why you need standards for networking containers and how the container network interface came to be. And then we saw a list of supported plugins available with CNI. In this lecture, we will see how Kubernetes is configured to use these network plugins. As we discussed in the prerequisite lecture, CNI defines the responsibilities of container runtime. As per CNI, container runtimes, in our case Kubernetes, is responsible for creating container network namespaces, identifying and attaching those namespaces to the right network by calling the right network plugin. So where do we specify the CNI plugins for Kubernetes to use? The CNI plugin must be invoked by the component within Kubernetes that is responsible for creating containers, because that component must then invoke the appropriate network plugin after the container is created. The CNI plugin is configured in the kubelet service on each node in the cluster. If you look at the kubelet service file, you will see an option called network plugin set to CNI. You can see the same information on viewing the running kubelet service. You can see the network plugin set to CNI and a few other options related to CNI, such as the CNI bin directory and the CNI config directory. The CNI bin directory has all the supported CNI plugins as executables, such as the bridge, DHCP, flannel, etc. The CNI config directory has a set of configuration files. This is where Kubelet looks to find out which plugin needs to be used. In this case, it finds the bridge configuration file. If there are multiple files here, it will choose the one in alphabetical order. If you look at the bridge.conf file, it looks like this. This is a format defined by the CNI standard for a plugin configuration file. Its name is mynet, type is bridge. It also has a set of other configurations which can be related to the concepts we discussed in the prerequisite lectures on bridging, routing, and masquerading in NAT. The ACE gateway defines whether the bridge network should get an IP address assigned to it so that it can act as a gateway. The IP masquerade defines if a NAT rule should be added for IP masquerading. The IPAM section defines IPAM configuration. This is where you specify the subnet or the range of IP addresses that will be assigned to pods and any necessary routes. The type host local indicates that the IP addresses are managed locally on this host, unlike DHCP server maintaining it remotely. The type can also be set to DHCP to configure an external DHCP server. Well, that's it for this lecture. Head over to the practice exercises and practice working with CNI in Kubernetes. Hello and welcome to this lecture.